Thanks, Paul. As Paul mentioned, my name is Raiza, and I'm doing my PhD over at Curtin University in the Space Science and Technology Center at the School of Earth and Planetary Science. And today I'm going to talk about impact craters, meteorite impact craters. Before I start, just a little breakdown. I'll first start with an introduction because I know this is not a topic that sort of everyone's keen into, and how they form, the effects that they have on rocks and minerals. Being a geoscience crowd, I mean, this is what I study as well. Being a geologist, there's many angles that you can study impact processes, but I focus on the effects on rocks and minerals. Then I'll go into the Australian, and I mean more focused on the WA impact cratering record, and after that I'll go into some new discoveries in WA and advances in the field. And sort of these themes are kind of intertwined, and you'll see that in the breakdown of what I'm discussing. So why we study impact craters? So impact processes are a fundamental process in space, and it has been fundamental in the formation and the evolution of our solar system, planetary accretion and so forth, as well as in shaping the surfaces of planetary bodies. For example, by studying impact structures, we can also gain insights as to the geology of other planets and moons in our solar system, and perhaps extrapolate beyond our solar system to other solid bodies, Earth-like planets in other systems. From a terrestrial perspective, because I mean this is what I focus on, is terrestrial impact craters. They help us understand early Earth evolution, and early Earth, early life, understand mass extinction, climatic events as well, and some are associated with world-class ore deposits. For example, nickel PGE from Sudbury are impact-related. Gold from Vredefort in South Africa as well have an impact history to those deposits. So a lot of different lines of reasons as to why we care and why we like to study them. When talking about impact craters, they're pretty ubiquitous in a lot of planetary bodies. Here's an example of the moon. They're basically holes in the ground formed by hypervelocity impacts, right? And depending on the body, they can range in size from tens of microns to thousands of kilometers. Basically, in the case of the moon and Earth and Mars, the distinguishing factors on the size and morphologies of impact craters and impact structures are the gravity of the planet, the mass and composition of the projectile, and the geology of the target rocks, so what's being hit. These are the main criteria that factor in how your final structure is going to look like. So this is the moon, but what about Earth? Here are some examples of Earth. On Earth, we really see things more like simple craters up to peak ring basins. And here's some examples from Meteor Crater in Arizona, which is about 1 kilometer in diameter. Goss's Bluff, which is about 22 kilometers in diameter. And this image really just represents the central uplift of that structure, not the whole structure. And the dinosaur killing event from Chicxulub in Mexico as a peak ring basin. All right. Before I move on, I just want to have a comment on preservation, because I will use the term impact crater and impact structure throughout the talk. And what I mean really is degradation or lack thereof. So when I talk about impact crater, is an impact which is more pristine. It hasn't lost its shape. It hasn't been highly degraded by tectonic processes or by erosion. And when I say structure, I'm mostly talking about something that's more degraded, heavily eroded. And usually, younger craters are less degraded than older craters. All right, so that was a little break. Now coming back into how they form, there's basically 3 stages, and the names of the stages are very self-explanatory. The first stage is the contact and compression stage, where the projectile hits the target and a shock wave is released. Melt is also produced in this stage. Then we have what is called an excavation stage, where material starts being removed. That shock wave keeps propagating. And here we make a distinction between those simple craters and complex craters that I mentioned before. So the process is similar, but looks slightly different when you start getting larger complex craters, where a rebound effect in the center causes a central uplift. So the final morphologies will differ. And finally, at the modification stage, the shock wave has already propagated through. And in both cases, at the start of this stage, we have an unstable, really high relief structure that eventually collapses. In a simple crater, you're left with a bowl-shaped feature filled with breccias and melts and just a jumbled up mess of rock. And in a complex crater, it's slightly different, that those rims then collapse, and you get these very distinct ring faults around the structure. So the shock effects are very significant on the target rocks, and they go beyond what we see in endogenic processes. The figure to the left is explaining basically the difference between normal endogenic metamorphism processes that occur within these temperature and pressure ranges. Here, temperature on the left, pressure on the x-axis. And the zone of shock metamorphism really starts occurring at really high pressures and can go up to really high temperatures. And I'll mention this in upcoming slides, but some of the features that form at these high pressures are the things that are diagnostic of impact and what helps us confirm if a structure is an impact versus a ring intrusion or a volcanic crater, degraded volcanic crater, something like that. In cross-section, what you would see sort of at that first stage, here is a sort of a radially distributed pressure. So that sort of reflects the radial expansion of that pressure wave from the point of contact of the projectile. And what that looks like in terms of what effects the rocks have is a melt right at the very contact, that shock metamorphism zone that's reflected in this field. And beyond that, fracturing and brecciation, and that would lack some of those shock metamorphic features. So continuing on the shocks effect that the rocks and minerals sort of undergo, there are several lines of evidence in the macro scale and also in the micro scale. In terms of macroscopic features, which is sort of things that we can just see at plain sight, shatter cones, which are these conical features, are the only diagnostic type of evidence that we can see of the shock effect onto a rock. Of course, meteoritic fragments around a crater are also a good sign that this has occurred by a hypervelocity impact, but sometimes it's a correlation rather than a casual cause and effect relationship. But there's tools about you can fingerprint rocks and then the meteorites themselves to try and correlate those events. Then in the microscopic scale, the mostly studied shock effect is deformation in quartz. So this is reflected as planar features, planar deformation features, and feather features. And this is an example here of PDFs, what we call planar deformation features in quartz. And these occur at crystallographically preferred orientations. So we know by experimental calibration that different crystallographic orientations represent different pressures that these minerals have undergone. In the case of this example of the 1013, that represents shock pressures above 15 GPa. So that's really, really good tool to try to understand your crater environment, where your rock came from within that impact structure or that impact crater. Then another microscopic scale diagnostic feature is deformation in accessory minerals, and this commonly is reflected as deformation twinning, again along crystallographically preferred orientations. In the case, for example, of zircon, this is a zircon that has shock twins. These are preferentially oriented 65 degrees about the 112 plane. And that's how we know that these were caused by a structure. A lot of this has been experimentally calibrated, and this is how we know. It's via experiments. We also have granular neoblasts, basically recrystallized portions of the grains, and phase transitions. For example, high pressure temperature polymorphs of zircon. In this case, in this mineral here, it's called reedite. Also, it's not something we see under a microscope, but the presence of a geochemical anomaly is also a diagnostic indicator of impact. So for example, if you study an impact melt rock or an impact melt glass and you study its geochemistry, it potentially holds clues as to a meteoritic component. So the most commonly cited is an iridium anomaly. Iridium is not abundant on Earth's crust. So you can tell if it comes from a meteorite and if it has a high iridium content. And I'll show an example of that in the upcoming slides. So now that you know everything about how they form, the shock effects, everything about impacts that you might ever want to know, I'm going to start going into the terrestrial record and the Australian record. So as you can see here, this is a map that represents all the impact structures that have been confirmed on Earth. There's about 200 confirmed structures, and you can see their distribution here. A lot of them are actually in Australia. There's about 33 impacts that have been confirmed in Australia. And that represents a high number based on how discovery rates in a lot of other countries. And of course, I'm going to focus on the Australian record because we're in Australia, and then more specifically in WA. But Australia is actually a really good place to study impacts because it's been relatively stable, even though some people might tell me that's totally wrong, but it's been relatively stable for a long time. And a lot of the landscape has been arid, so there's been less erosion of structures and features. So that's why we love studying in Australia. There's also a bit of a sampling bias because we have so much resource, right? We have resources to go explore these things, which is great for me. So this is what the Australian impact record looks like generally. There's a ton. As you can see instantly, a lot of them are concentrated in WA. There's about a little over half of the impact record is held within WA. I mean, having two cratons, even though maybe this one doesn't matter as much, kind of helps a lot of old rocks. So when I say about 33 impacts have been confirmed, you think, why are you saying about? Why is that an approximate? The reason I say that is because there's actually a few structures, for example, Picaninny, Connolly Basin here, that have been historically accepted, but we still need diagnostic features to be found. So it's a good opportunity to do some more studies here. Also, another thing is that the most recent discoveries, confirmations, Orbanda and Ilkerka, haven't been published yet. So they're sort of crossing the line into that space. So beyond the confirmed record, there's also a huge number of structures that have yet to be confirmed. So a lot of these are possible impact structures, and some that have been contested in the literature. There's about 49 structures. You can see them represented in the white circles, and they're actually labeled in this map. The confirmed ones are not labeled. So again, there's huge opportunity for study in this realm. When we look at the size and age distribution of these, in yellow are Western Australian impact structures. Few are young, less than 1 million years of age. And a lot of them are actually pretty old. Nearly half of them are Precambrian. And some coincide with major events. For example, last Paleoproterozoic glaciations, and then the Lawn Hill coincides with the Ordovician cratering spike. So there are some sort of geological time frame relevancy to some structures that have occurred on Australia, some events that have occurred in Australia. So moving on to Western Australia, because you have the best record. There's 16 impact craters and structures that have been confirmed. Most of them are exposed at surface. Few of them are buried. For example, buried structures include Ilkerka, Yallowlee, Woodley, and Rayside. Most of these studies and discoveries come from acquisition of drill core, either from survey stratigraphic tests or exploration, private exploration. The only one that doesn't fall in that category is Yallowlee, which is actually discovered being proximal ejecta layers where the shock minerals were found. Most of them have been confirmed by the discovery of either shatter cones, that macroscopic deformation feature, or shock minerals, either quartz or most likely zircon. And few of them have had meteorite fragments discovered. And of course, these ones, it makes sense that meteorite fragments have been discovered because these ones fall within some of the most young structures. So there hasn't been enough time to weather out those meteorites. Let's come back to that. Yeah, and that's the Dalgaranga, the Beavers, and the, I don't know if it's world famous, but the pretty famous Wolf Creek. Once I go back to the other hemisphere, I'll make sure it's world famous. Some of the impacts have been studied for quite a while, and some of the earliest discoveries were Wolf Creek, and this is again focused on WA. So some of the earliest discoveries here are the Wolf Creek and the Dalgaranga. And then through the 70s and 80s, a lot of progress was done in discovering and confirming some more craters and structures. I stopped in the 80s because that's when I was born, and I really don't want to say that anything beyond that is recent or not recent. So that's why I stopped there. It's a bit of an arbitrary pause in the history of discovering impacts. But that's my own bias. I just need to be very vocal about it. Most recently, and I mean really in the last 5 years really, some of the highlights in the study of impact craters in WA have been the study of shock effects in oblique impacts. That was done by Cox et al. In Spider. So there's not a lot of oblique impacts recorded on Earth. So studying their morphologies, mapping, and studying how the shock effects are distributed are really providing insight of how a lot of these structures may have looked like, even ones that are just no longer present because they've been eroded. New age constraints have been provided from Wolf Creek and Yarrababa. Very different ages for these two. Wolf Creek was previously thought to be 300,000 years old, so it had occurred that long ago. But new beryllium exposure age dating has determined that it's actually 120,000 years old. The Yarrababa here in the Yilgarn has new uranium-lead ages and of 2.2 billion years. Basically, as far as we know, this is Earth's oldest impact that is known so far. So it's right here in our backyard in WA. Also, the first documented occurrence of rhyolite, that high-pressure polymorph in Australia, was found in WA in the Woodley structure. And new sites have been confirmed and or discovered. Newly confirmed are Yallowlee and Ilkerka. I don't say newly discovered because the possibility of these having to be impacts had been proposed previously, just no diagnostic evidence had been found before. Orbanda is actually a more recent discovery. It's also out in the Ilkerka, in the eastern goldfields. And I'll talk a little briefly about some of these in the upcoming slides. So Orbanda, I already showed you where it's located. It's actually a 5-kilometer diameter structure. It's buried, so you can't really see a morphological, well, it's partially buried, so you can't really see a morphological expression on this map, and it's near a few mines in the surrounding area. It was first targeted as an exploration campaign out there in the gold fields, and you can see a gravity anomaly, sort of a gravity low with a central gravity high. 2 boreholes were drilled by evolution mining, and seismic and gravity surveys were conducted by resource potentials in 2018, around 2018. And you can see sort of a circular gravity anomaly, and then in the passive seismic, you can also see a bit of a crater morphology where you have higher sides with a moat-like area and an uplifted center. And of course, the geophysics really aren't diagnostic. They could have potential different origins. But during the drilling campaign, shatter cones were identified by Myers in the drill core as well in the surface. We went back and surveyed and found more shatter cones in the surface. And doing petrography revealed shock quartz within brecciated samples from that core. Again, shock quartz with PDFs being diagnostic of impact. Another really cool discovery within Orbanda was the presence of Suevite. And Suevite is cool because it's a breccia, and polymaker impact breccia, that contains impact melt glass. And that's sort of what that qualifies it to be a Suevite. Here's an example of what it looks like in core. You come in from a polymake breccia, looks like a regular breccia, into this area where you have these fragments of glass within the breccia itself. This is what it looks like in thin section under plain polarized light. And you can see it was pretty distinguishable glass along the matrix, and even a partially melted clast, where you had pretty intact rock in the center and glass at the rims. So geochemical analysis of this glass, impact melt glass, by laser ablation induced coupled plasma mass spectrometry revealed, LAAICPMS has revealed that there is a high concentration of iridium. And when you compare that to iridium and chromium, you can start making some correlations, and you can start to see that, first of all, the glass is very different from mid-ocean ridge basalt, sort of like general crustal rocks, upper continental cross, and also very different to some of the basalts that are in the vicinity of the impact, the Victoria's basalt and the bent tree basalt. Another really nice feature of this type of display is that we can also correlate it to data from meteorites and try to see what type of projectile was the impactor for this event. And they mostly correlate with an iron meteorite prediction for that projectile. Moving on to another recent discovery, which is the Ilkerka. It's way east in WA, within the Officer Basin, really pretty remote area. And it was previously reported as having a suspected impact origin by Yaski and Glickson, and was recently been confirmed. This structure has been suspected to be of impact origin, basically because of its morphology. So this is a total magnetic intensity map, and Ilkerka is down here at the bottom right. And you can see it has a ring-like magnetic anomaly. And there's a few others in the area that haven't been explored that have a similar feature. When you zoom in, you can see that it's actually about 3 different ring-like circular anomalies with a total diameter of approximately 12 kilometers. And it was also drilled in an exploration campaign by Maria Resources in between 2019 and 2020. So in collaboration with the company, we were able to access core and study it. So from studying the core, some of these sort of very deformed brecciated sandstones, we found shock quartz. And I've shown this grain. I'll show it again because I really like it. It's the confirming grain for the structure. And it records PDFs that represent pressures of over 15 GPa. So that's under interpretation at the moment. So that's just sort of some of the newest discovery. And I'm going to move on to some of the advances and intertwine again, as I mentioned, with discoveries in the recent years. Before I talk about advances, I really need to give credit to the classics. I mean, there's nothing like a good field study. You could sort of recognize morphologies, try to see if there's shatter cones, discover meteorites. And I mean, who doesn't like to be in the field? Also, petrographic studies is how we try to identify quartz. And it's also very accessible. It's something that we can do with petrographic microscopes, and you don't need super fancy technology. You do need an expert in universal stage analysis, so someone that can sort of measure the orientations of those features. But again, still very accessible components of the study. And again, geochemical approaches. So some of the new things that have been in the realm of studies are things that aren't totally new concepts, but have advanced in the past decade. For example, there's groups that study digital elevation models of impacts to such a high resolution that they can sort of map on images. It doesn't replace actual field mapping, but it could be a good start. And there's actually a global atlas that's been published. Unfortunately, it costs money. But if you're really interested in that component of the study, I think it's well worth it. These models are basically built by remote sensing, which I think is also really cool that we've gotten to this level of resolution in this type of study. I don't have a image for it, but shock experiments have also advanced a lot in the past few years. And they help us calibrate shock features to pressures and temperatures, how they form, because we can confine that into experiments. Also numerical modeling, which is represented here in the center. I'm just going to go back and try to play it again. Oh, I guess it doesn't go. This is a code that basically allows us to parameterize and simulate impacts. So basically impactor velocities, target rock lithologies can be parameterized to try and either correlate to known impacts or sort of predict types of impacts that we might have seen in the past. It's used a lot in the study of impacts in the moon and in Mars. And then last but not least, electron backscatter diffraction analysis is basically an SEM-based type of analysis that we use to study deformation in rocks. And what it looks like is if you have a scanning electron microscope with an electron beam coming from here, hits your sample, which is tilted at 70 degrees, and those electrons are actually diffracted in a pattern. And that pattern is basically crystallographically controlled, so you can then tell about phase, what phases you're looking at based on those electron diffraction patterns. You can study misorientation that basically gives you insight into deformation and even strain. And Oxford has built this capability. So this is not brand new, but what has advanced in the last few years is first the resolution of how we can map minerals through this technique, and also the acquisition times. So what you see in the background here is a large area map, we call it, and it's thousands of zircon grains that have been mapped using EBSD over a few days. So from a map like this, or like this, if it comes through, or like this, you can thus select targets for further study. So it's a good first pass as to trying to understand if your mineral is deformed or not, to then do more advanced studies. For example, trying to determine if it's shock twinned, if it has neoblasts, so newly recrystallized portions of the grain, or even if it has phase transitions that are also crystallographically controlled. So yeah, it helps us find shock minerals in sort of a needle in a haystack type of way. But it also, given that we now understand that a lot of these, thanks to this technique, that a lot of these neoblastic portions are newly recrystallized, basically they can reset your uranium lead system at time of impact. That means that now we can date impacts. And I don't know if you remember, I can show it again later, the uncertainties on the impact ages that I showed in that chart, the uncertainties are pretty wide, like sometimes in the order of 1 billion years. So the fact that this technique has been developed and is now pretty commonly used is great, because then we can study the impact record more detailed and correlate it better to other geological processes that have occurred during the evolution of Earth through the geologic timescale. So this is an example from Orbanda. I mentioned before, it's the Earth's oldest known impact, where there's shocked zircon and shocked monazite. And these were targets for dating. And this is how we know the age of that structure. So here are some of the results. This is from Erickson and the team in 2020. It's been determined based on monazite and zircon. The lead 7-6 ages sort of around the 2.2 billion years. And it's represented here. The structure is, again, out in the Yilgarn in WA. It's about 70 kilometers in diameter. And thanks to the integration of these techniques, that now we know the impact age for this structure. And we can now apply this technique further to other structures around WA, Australia, and the rest of the globe. Another sort of correlation that was made during the study was that it was recognized that this impact occurred contemporaneously with the Raizian period. And this was synchronous with the termination of glacial conditions. So there's a correlation there. Again, not necessarily causal, but it's very interesting as we get more precision within these dates to sort of understand how it can correlate to other events that have changed either local climates, regional climates, or global climates. So in summary, the Australian impact record is awesome. It's about 15% of the global record. It's super valuable scientifically, just because there's so much to study and there's such a variety in age and size and distribution of impact structures. It also has cultural significance. The Wolf Creek crater actually has been recorded in oral traditions of First Nation groups up in North WA. And I encourage you to look up the art for the Wolf Creek and the origin story online. I didn't want to put some art here because I wasn't sure if it was appropriate or not. But I really encourage you to go look at it. It's really cool. And there's so much opportunity. So a lot of the sites that are confirmed are actually underexplored. It's like, oh yeah, impact, great, awesome, shock quartz, goodbye. Or So there's a lot of potential there to understand impact structure, impact processes in general, and do some of these integrated studies. Also, what else is buried? You know, we already know that there's several sort of ring-like anomalies out there. Could they be impacts? So that can also help understand not just Australian records, but the global records and impact cratering rates and things of the sort. And honestly, we keep pushing the limits of technology, and that's awesome. That's what we do in research, and it's really, really awesome to be a part of it. And before I finish, I encourage you to check out some resources for more details on accessory minerals and some of their use as geochronometers and their shock features. I encourage you to check out Aaron Cavosi's talk, which is in the GSAWA's YouTube channel. And also some impact record publications for Australia. And with that, I'll take some questions. Thanks.